thunder and I am the lightning. Oh, is this thing on? Okay. All right, here's your Chapter 8 test review, FST kids. I'm just going to go through and actually do this whole book test thing here like I did last time, and I hope it doesn't take 5 videos, because you probably have something better to do with your life than watch this for an hour and 15 minutes. Okay, so here we go. Remember, these has been a while. We've been spending so much time on the 8.4 to 8.9 stuff. This is back from near the beginning of the chapter. This is a recursive formula, by the way. Recursive formulas is when you have the two liners kind of thing, and they have to tell you what the first term is, and then they have to tell you how to get from any term to the next term. This n-1 thing is the previous term, and then this would be how you find the last one. If you're going to do this on a calculator, I would say what this basically means is ants minus a half ants. It's kind of like, that's how you would put that in the calculator, and you'd hit enter, 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 and you'd get the list of the sequence after you had 5 in as your first answer. You know what? Let me show you that. Okay, here you go. So here you go. This is 5. Now that's in there, sort of stores my answer. And the thing I had here on the recursive thing was answer minus a half of the answer. So you can just go answer minus half of the answer. And here comes the sequence, 2.5. It's going to do that again. Notice it's going to take the current answer and now stick that in here, and we get the new one. So that's what the sequence looks like if you want to just see it really fast. I let that go by too fast. I kind of forgot what the first couple ones are. Anyway, so the first thing we're supposed to do is write the first 5 terms. That's a sub 1. A sub 2 is, well, I would take, and you can do this one in your head, it's easy enough. I do 5 minus half of 5. Why don't you just cut it in half? Take the thing minus half itself. That's kind of silly. All right. Then I would take 2.5 minus half of itself, which feels a lot like divide by 2. Again, I don't know what this is about. Oh, I know, because they're trying to confuse you, number 2. Ah, pretty sneaky. All right. A sub 4 is 1.25 minus half of itself, which is 62.5%, I think. And a sub 5, I could probably get this from the calculator now. Yeah, 3.125. Aha, so they kind of disguised this in a recursive formula, but what do we have going on here? I said, yeah, if you take anything minus half itself, it's just like, it could have just divided by 2 in the first place. You see what's going on here? 5 divided by 2, divided by 2, divided by 2. Get the same sequence, which means it's geometric. It doesn't ask for this, but if you wanted this as a geometric explicit formula, what's really happening here is I'm taking constant ratio of half, which is how this goes, and the initial term, the g sub 1 here, which goes in the front, the g sub 1 here is 5. So that's the geometric series we're talking, or sequence we're talking about. All right, we're evaluating series to the nearest hundredth. The only formulas we have for how to do the series is real slick-like, is to have them either be arithmetic or geometric. So the first thing you do is sort of figure out what kind we're dealing with here. And this is tougher than that's been on the quizzes, because now they're scrambling up the arithmetic ones and the geometric ones. Arithmetic would be the ones where there's a constant addition going from term to term to term, and geometric is the one when there's a constant multiplication going on term to term. And you have to kind of look at the series and figure out what you got. Here, supposing it's addition, this would have to be plus 2.3, right? Yeah, and plus 2.3 looks pretty good. Looks like we're adding plus, it's the plus 2.3 sequence. I'm adding 2.3 to the previous term. That's kind of a recursive way to think of that. So for number 3 down here, for the sum of arithmetic, I'm going to look at my formula sheet, which, by the way, you will have. For the arithmetic sum of series, it's this. N over 2 times 2a sub 1 plus n minus 1 times the common difference. Well, I found the common difference right away. That was the 2.3. A sub 1 isn't tough. It's right there. What's tricky here is what is n? N is, how many terms are there here, and I don't know what this is. I think I'm going to go for the explicit formula to try to figure that out. Remember, the explicit formula is what you use when you want to jump right to a certain term. It also works sort of backwards. I know that a sub n in a arithmetic series sequence, is always, sort of this part, n minus 1d. And in this equation I can figure out what n is, because I know what a sub n is. It's 126.1. I'm going to run out of room here. 126.1 equals a sub 1, and I know what that is, plus I don't know what n is, but I know what the common difference is. And I can figure that out for n. I think the first thing I'll do is subtract 6.5. Oh, yuck. I'm kind of embarrassed, but I'm going to do this anyway. I guess worse would be making a mistake on video. 119.6 divided by 2.3 is going to be n minus 1. Okay, so divided by 2.3. I don't make another calculator mistake like I did last time. 52 is n minus 1, so n must be 53. Okay. So that's good. So now I can apply this. In this situation, can I just kind of do this over here? In this situation, what I have now, since I know that this is a sub 53, I can figure out all of this stuff. I have a sub 1, I have, all the stuff I mentioned before. So this is 53 over 2 times 2 of the 6.5s plus 50, can I say 52? Are we cool with that? N minus 1 d. And if I do that all in the calculator, I can move this over so I can, oh, can you see both things? Whoa, 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 what just happened? Okay. 52, 2, yeah, I can't really make it so I can see all that at once. So I got to take 52 times 2.3. Then what am I doing to that? I'm adding 13. Oh yeah, I know that's 119.6, duh. And I'm taking the whole thing times 53 over 2. I think I did that right. It's 3513.9. Okay, and there we go. In number 4, I have to figure out what kind of sequence I'm talking about here, first of all. And I mean, you might look at this and go, oh, I can tell because of the way this looks with the exponent and that kind of stuff. And I know I'm adding up the first 32 terms. But I think it's safe, and it's not a bad idea to kind of estimate and get your head around it if you have an extra second. So go ahead and write out the first few terms of this and see if you can tell what kind of sequence we're talking about. The first term happens when I put n in as 1, so that would be 14 times 0.09 to the 0 power, which is 14 times 0.09 to the 0, which is by itself, that this part would be 1 here, so that's just 14. And then it's a summation, so then I'm going to add the next term, which is going to happen when I put in 2 for this. 14 times 0.9 to the first power looks like this. Whoa, it's a 9. The next term would be 14 times 0.9. Now this is n equals 1, n equals 2, n equals 3. This would be squared. I'm not going to actually do this. I think I have enough. I have enough here to see actually what this is going to look like. 0.9 cubed. You notice what's happening as I go term to term here. If I was going to try to recreate this in my calculator by going answer, 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 equals, 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 you notice each time here it's just being multiplied by another copy of the 0.9. So this looks like a times, come on, decimal point, times 0.9 kind of thing. Each time I'm going from one term to the next, I'm multiplying by another 0.9. Okay, so this is geometric. Great. Well, they gave you 2. There's only 2 types we can add up. You might guess that one of them is going to be arithmetic, one's going to be geometric. Okay, so the sum of series formula for geometric is a little prettier than arithmetic. It's, generally speaking, g sub 1 over, times 1 minus r to the n. There's no minus 1 there, which is sometimes tricky, over 1 minus r. Okay, which here is 14's first term. That's why it's kind of nice to have that written out, because then you don't have to go back and think about this much more anymore. 1 minus r. Now the r is the thing that's being multiplied each time, and the thing that's being multiplied each time is 0.9, remember. So as I multiply each thing by 0.9, that means this is what goes here. This exponent is just on the 0.9. And it's how many I'm adding up? Well, I'm adding up from 1 to 32. So there's 32 there for n, and over 1 minus 0.9. Which you can do in your head, that's 0.1, which I always do that part in my head on the calculator. Okay, 0.9 to the 32th power. Yes, that was on purpose to be funny. Okay, 1 minus that. That's how I do it in the calculator, so I don't have to memorize any decimals. And it was 1 minus that times 14. When the whole thing is divided by 0.1. That's 1 minus 0.9 right there. 135 point... Gosh, do I really care? You know what? That's probably a nice fraction. Oh, I thought... Oh, not really. Okay, we'll leave it as decimal. 195, because it was a decimal. It was framed as a decimal in the original part of the problem there, so... All right, 135.1... Does it even say? Ah, 100. 135... Point, is it 19 or is it 2? It's 19. Okay. Okay, there we go. Okay, this is about the sequence converging or diverging. So this is where you got to be really careful that you're not talking about series. This isn't talking about adding these up onto infinity. It's just talking about what happens to this number itself as I get larger and larger values for n. What's happening to each term? Is it getting closer to something, or is it going infinitely crazy? Here in 5, if I have something like 56 times 8/7, which is bigger than 1, by the way, to the zillion minus 1th power, well, 8/7 to some enormous power is really going to be a huge number, right? Anything over 1 to a large power is going to grow infinitely huge, and we have it times 56, so this one is definitely going to be divergent. If you don't believe me, or if you're not sure, or if you're trying to figure out something like this on the calculator, you can get this to show up in your calculator as, yeah, you can put it in here. It's 56 times 8/7 to the power of, and yeah, you could say x minus 1. Why not? Now remember, this is only really defined for whole numbers, so I care about the graph, or sorry, the table a little more than the graph. Fine, so I'll go, what's my table look like right now? I'm at 8 going up. So 8 to 14, I mean, it certainly doesn't look like it's slowing down at all. You can use table set, you could jump. Let's jump to the zillionth power. Well, we can't actually type zillion. Let's jump to the, I don't know, 1,000. See if it's getting any, see if it's settling down. See if it's gravitating towards some number by then. Doesn't seem like it. These little e's in here, and if you can see, that means we're talking about times 10 to the power of. So this is really a huge number. This is 4.8 times, if I have that highlighted, it's 4.8 times 10 to the 59th power. So this is like 4 zillion already. Then we get 5 zillion, and then we get 6 zillion, and it keeps going, and then we have another power of 10 by here. So yeah, this is crazy. This is not coming back to reality. I'm only up to 1,000. So on up to infinity, that's going to continue to get more and more ginormous. Why did I do that? Okay. 6. Well, again, they give you two 50-50 questions. What do you guess? I bet this is going to be convergent. But finding what this converges to is a little bit tricky. You look at this sequence here and go, oh my gosh, what are they doing? Well, good thing they showed you the rule here. They're doing that. If you put in 1 for 5n minus 3, you get, and over 7n minus 3, you actually get 2/4, which reduces to 1/2, and etc. down the line. But they give you this to kind of give you an idea what it looks like. It's a half, and then 7, and then 2/3, and then 7. So it seems to kind of, was that right? If n is 2, is this really 7 over 1? Yeah, that's 1. And the top is 10 minus 3. Yeah, that's sure enough, that's 7. Weird. They reduce sort of randomly. There might be some other bigger ones down here. But eventually, what does this turn into? Well, it's 5 zillion over minus 3 over 7 zillion minus 3. In the end, I think the minus 3 is not really going to matter. You have 5 times huge minus 3. Like, okay, if it's a million, it'd be like 4,999,997 over 6,999,997. So it really starts to look like 5 million over 7 million when you get huge. So you might guess from that right there what the answer is going to be when it starts to always be stuff like 5 million over 7 million. But if not, you can always apply the divide top and bottom by n kind of thing, because it will become an equivalent fraction. 5n over n is actually 5, and then this becomes 3 over n. 7n over n is actually 7 minus 3 over n. Now we have something when n goes to infinity. Think about this. This 5 isn't going anywhere in the sequence now because it's not affected by n at all. 3 over n will become 0 as we go on and on and on, because 3 divided by a zillion is really tiny. Same thing down here. So really the limit of that thing is now starting to look like 5 minus 0 over 7 minus 0. Another reason to tell you that This is starting to look like 5/7. If you didn't like the million argument before, where it looked like almost 5 million divided by almost 7 million, and as it gets bigger, the almost starts to get even closer, then here you go with the over end business. All right, that's my time's up for this one. I'll see you in part 2.